Hello and welcome to this podcast coming to you from Mrs. Walton's room in the Science Hall at Pamlico County High School. Today we're going to talk about waves. You should have already done an introductory activity where you learned some basics, but today we're going to learn a little bit more and fill in our notes. So you should have in front of you your student notes on waves. If you don't have that, you should probably pause this and go find it and come on back and start up again. So, what are waves? You might think of ocean waves or sound waves, and those are all waves, but what their main purpose is to carry energy from one place to another. Every time there's a wave, there's some sort of energy being transferred. And we have some main types of waves we're going to talk about over here. Transverse, longitudinal, surface, and electromagnetic. We'll talk more about those as we go. And in this picture here, you actually have a sound wave that's being amplified from a speaker. So what are some examples of waves? Well, right here we have a ripple. This is a wave that's moving through water. Like I said before, here's a sound wave. Over here we have a wave on the beach. And of course, right here is our electromagnetic spectrum, which is on your reference sheet that you get to use for physical science. And there are multiple kind of waves here, so you can choose anything you'd like for your examples of waves. Now, how about what a wave moves through? We call that a medium. If you think about the word medium, okay, it kind of means in the middle. And also, if you think about someone who is a medium, like someone who talks to ghosts, they are the matter that the ghost has to travel through to communicate with their loved ones, if you believe in that stuff. So some of the mediums that we know about that matter travels through include water, like in this picture. Here's a picture of outer space. That's technically a medium that matter travels through. Our atmosphere is a medium. And here's just another picture of outer space for you. So those are some great examples of mediums. How about the parts of a wave? Well, right here we're actually looking at a transverse wave, which we're going to talk about in a minute, but you need to know some important parts. The distance between these two spots right here, or these two crests, is what we call the wave length, which makes sense because we're going from the start of one wave to the very start of another wave. So that's our wave length. We also have, like I mentioned, our crest, which is the top, and this guy down the middle, which we call our midline. And down here at the bottom, we have the bottom of our wave, which we actually call the trough. Now, what do we call this guy that number 2 represents? It's like the height of the wave. Well, that's our amplitude. Have you ever heard of an amplifier? It increases the height of a wave. So label all these parts on your little diagram and be sure to commit those to memory. Now, first of all, we're talking about the types of waves, and one of the main types is a transverse wave. The thing about transverse waves is that they vibrate at right angles, which we call perpendicular. If you recall back into your math knowledge, perpendicular looks like this line that's sticking up at a 90-degree angle from the surface below it. And that's exactly what's happening right here in this transverse wave. So think about taking a slinky and just swinging it up and down, or a rope. That's what a transverse wave looks like, and the wave moves forward. And I have a little interactive here for you that I'm going to show you for transverse waves. So let's watch this little dot here and see how a transverse wave works. And this line is tracing what the transverse wave does. It just goes up and down, up and down. So transverse waves, just like that slinky, where the vibration travels through the wave, or through our medium. What would be the medium if we were moving a slinky? What would be the air in the room? Think about if you tried to vibrate a slinky underwater instead. It might be a little more difficult, but it would still be a medium. So medium can affect the way that waves travel. That's a good example of a transverse wave. Now what if we make multiple layers of our transverse wave? This gives a really good diagram of the way the waves move up and down, perpendicular to the surface. These guys are moving up and down or perpendicular. Alright, so that's a transverse wave. Now what about a longitudinal wave? This is one that we say moves in the same direction as the wave. We also say that this one moves parallel to the surface. So let's add that into your notes. It moves parallel to the surface. Okay, and we have a couple parts of this wave that we also need to label. This part right here where it's squished together, like when you squish together a spring, is called compression. And this part where it spreads back apart, like after you let go of the spring, that's actually called rarefaction. You might think of refraction, that's different. Rarefaction means it's the opposite of compression. It's speeding apart right here. And I label those on your wave, and then I have another example for you. Here's our longitudinal wave. Let's just look at one layer to start with. Notice that my dot is simply moving back and forth. If you compare it to the surface, and we can consider any of this the surface, it's moving parallel. Whereas our old one, transverse, was going up and down. So let's compare transverse to longitudinal. This is like if I lay my slinky flat on the table and I just push it forward. What happens? Well, all the energy goes to one end and then bounces back. Where it's squishing together, it's compressing. What did we call it where it spreads out? Rarefaction. So it's rarefacting. And here's a good example of how that works if it's a bunch of layers of molecules. Okay. Now, let's move on to surface waves. Surface waves travel along the surface in small circular motions, and the best way to think of it is an ocean wave. The particle stays in the same place and moves around and around and around again. This is like being on essentially a river that doesn't have a strong current, and you can stay in the same place on your inner tube without moving, or sitting out in the ocean. Your boat can stay in the same place without moving too much in one direction or the other. That's thanks to surface waves. So let's look at a little diagram over here of how surface waves work. The wave almost looks like a combination of transverse, which was up and down, and longitudinal, which was back and forth. And what it causes is this little molecule to move back and forth in a circle. That's exactly what's happening in a surface wave. Let's look at many layers of that. This should look very similar to what an ocean wave looks like. Have you ever stood in the surf when waves were crashing and you felt pulled back out into the ocean? That's because the medium that the wave's traveling through, the water, is pushing back out just like it is in this diagram and pulling you back towards the ocean water. So let's compare the three since we've covered those. Transverse goes up and down, perpendicular through the medium. Longitudinal goes back and forth. And surface moves in a little circle, circular motion, right there on the surface. Alright, hopefully we have a good grasp on our waves now. What was the other one we talked about on that first slide? It was electromagnetic. And you might remember talking about these in the energy section. Electromagnetic waves are really unique in that they do not need a medium to travel through. Do you remember what a medium is? It means it's something that the wave is traveling in, like water or air or our atmosphere. So electromagnetic waves can travel in outer space or in a vacuum. And I'll define what a vacuum is here in a minute. But first, I want you to look at this electromagnetic spectrum, which is also on your reference sheet. Unfortunately, it's not in color on your reference sheet or on your note sheet. But what we should notice from this diagram is that radio waves have a wavelength or distance between crests of 10 to the third. That means move your decimal 3 times. That's really big wave. Radio wave can be as tall as a skyscraper. And those are the ones that go to outer space when you send a text message, okay, so that the person can get it. So big giant radio wave. Microwaves, like, yes, literally the ones that cook your food, are still decently big, but a lot smaller than a radio wave. And notice that as we go along to infrared, which is what you can see with at night, down to the visible, which is spelled weird here, but the visible light range, which is the colors that we see of the rainbow, down to ultraviolet, our wavelength is getting a lot smaller. Okay, what else is changing is our frequency, which we'll talk about later. So you can see that the radio waves are the biggest, the gamma rays are the smallest, which we talked about in the nuclear chemistry section, and visible's right in the middle, where here's what we can see in our visible spectrum, and this is actually zoomed in on it. Have you heard of Roy G. Biv? Add that in on your sheet there. R is red, O is orange, Y is yellow, G is green, B is blue, I is indigo, which is like almost purplish right here, and V is violet. So it's a nice little shortcut for how to remember. Now if you were to look at these, which ones would have the greatest wavelength? Well, I'm going to look furthest to the left because I know radio waves are the biggest. They're biggest skyscrapers. And my red would have my greatest wavelength. Which one would have my smallest wavelength? Other end, violet. If you remember Roy G. Biv, it's easy to remember that. Okay, so what did I mean by vacuum? Did I mean my mom just told me to vacuum the living room? That's not what I meant. What I meant was a vacuum is this space that has no matter in it. There are no solids, liquids, or gases. It's just like outer space. And the only thing that can travel through there is the electromagnetic spectrum. Any of those things in the electromagnetic spectrum. Alright, so we also want to talk a little bit about how waves act. Okay, and there are 4 ways that waves act here: reflection, refraction, diffraction, and interference. Now the first one is reflection. And this is when a wave bounces off a surface and it cannot pass through. So if you need to pause here, make sure you write this down next to number 1 under how waves act. And you might also want to draw a little diagram showing that it bounces off. What's happening here in this picture? Well, the flamingos, which if you look are at the bottom of your page, it's hard to see, but it's the second picture. They're having a reflection of their image that's coming off the water. We're pretty familiar with reflection, but that's when a wave bounces off a surface. The second one is refraction. This is when a wave bends when it enters a new medium. So compare your 2 mediums here. This medium's air and this medium's water. What happened was the ray entered and it bent, and what we say is that it refracted. Well, that's what happens when you see these images of a straw that looks like it's broken. It's actually completely straight, but the waves are tricking your eyes into thinking it's bent because the refraction of light as it enters that medium is changing the direction that it looks like our straw is going. And that picture is also on your page there, so make sure you label that. Next we have diffraction. Diffraction is when a wave bends to go around an object. I like to think of when there's a keyhole or a crack in the door and the light's coming through it into a dark room. That's exactly what's happening with diffraction. This wide gap here barely affected the way my light changed. But let's compare it to this little gap. You see a huge change in the way light looks when it comes through the cracks. And there's a good example in this picture of diffraction. In this one, we have a pretty large wavelength coming and a large doorway, but it's still diffracted. So it always bends when it passes through. In the next video, we're going to talk about interference. So make sure you come back and click the next video after a short break. See you soon.